So in this lecture, we'll be discussing about SIL verification using Markov analysis. Markov analysis is one of the most sophisticated method of doing SIL verification as on today, and this analysis or this method has been used in the backdrop of many softwares like Excellentia to do the SIL calculation. But Markov analysis is often thought to be very hard to understand, and many people take it like confusing sometimes. So in this lecture series, I will be trying to explain Markov analysis as the easiest way and try to make you understand about this topic. So let's begin with it. So uh, SIL verification and related functional safety issues are mainly governed by the two standard IEC 61508 and IEC 61511. And this Markup analysis is basically supported by both of these standards. There is another standards which is ATEX 50495. So that is mainly related to identifying the explosion risk of the devices, and that also use the Markov analysis. So this Markov analysis is basically came from the name of the famous mathematician Andrei Markov, who is a Russian mathematician who studied probability while teaching in San Petersburg University in late 1800. He defined the Markov process in which the future variable is determined by the present variable being dependent from the predecessor. So, uh, so just take an example. Just take an example of a ball moving, suppose with a speed in a particular direction, right? So, if we know the direction of the ball and the velocity of the ball at time t is equal to 0, we can predict what will be the velocity of the ball and the direction of the ball at the time t is equal to 1, right? So we need to know these two parameters properly, then we can identify. So if we know what is the state in the previous time, we can calculate the what is the state that can be in the future, right? And this is from where we get it. We get it from Newtonian mechanics, right? So from this Newtonian mechanics, we get that if we know the velocity and direction of a ball at a particular time t is equal to 0, we can predict its position at time t is equal to 1. But we need to know the previous state. We need to have sufficient information about previous state, that is t is equal to 0. So why Markov analysis is used in SIL calculation? So Markov analysis is a method that is used to forecast value of a variable whose predicted value is influenced only by its current state and not by any prior activity. So if you see uh, any situation, any SIL loop, so normally the behavior of the SIL loop, it depends only on its previous state, not like what has happened before or maybe 1 year before. That does not really influence it. So that is one of the reason of using Markov analysis in SIL calculation. In essence, it predicts the random variable based solely upon the current circumstances surrounding the variable. So this is one of the I would say this is one of the easiest and simplest technique to determine the future state of the components in the sieve, components in the safety function. So this is why this method has been widely used in SIL calculation. So in the next couple of slides, we will begin from very basic and try to understand how actually Markov analysis is predicting the future states. So take one simple example in which a system is in uh, initial state, that is t is equal to 0, and at that time it is working fine, it is in the 0 state, and now after a certain time it is going to in the fail state, right? And failure is denoted by state 1. So there are two states, state 1 and state 0, and there is a transition that is going on from state 0 to state 1 with a probability of lambda. We have assumed that there are only two states for this system and the system is non-repairable, which means once a component fails, it cannot be repaired back to its original state, which is OK is equal to 0, right? So what is your probability? So this, if this is the situation at time t is equal to 0, there is no transition. So probability p0 is equal to 0 is equal to 1, and p1 at time 0 is equal to 0. Now what will happen at time t is equal to say 1 hour, and this failure rate we can assume it is 0.1 failure per hour. So we can define that the probability P01, that is this item, so some components have failed and it has transitioned into the failure state. So what is the probability that a component will remain in this stage? This is obviously 1 minus lambda. So 1 minus lambda is multiplied by P0 is equal to 0 gives you the probability of the system to remain at 0 state at time is equal to 1, right? Similarly, initially there was no component in the failure stage, but slowly some components are failing and they are coming to this stage, right? So uh, so we need to add this initial, what is the component that is initially there, and then uh, how many components are getting basically transition into this stage, that will be lambda into p0 into 0, right? Similarly, if we take like p1 is equal to time 2, it will be obviously p1 into time is equal to 1 plus lambda into p0 is equal to 1. Similarly, we can say that p3 is equal to p1 into 2 and lambda into p0 into 2, and so on. So I have basically used this formula and done 10 iteration, right? So if you see, these are the 10 iterations. So this is the 0 beginning and we have done 10 iterations. So initially the probability is 1 and 0, then it gets multiplied by this value, so then it becomes zero point 0.9 and this becomes 0.1. Then again it is obviously 0.9 into 1 minus 0.1, so it becomes 81, right? And what, how this coming, this is coming 0.1 plus 0.1 into how much it can transition, because it is from 0.9, right? So it is 0.1 plus 0.09, so it is becoming 0.19. So this is how this particular value is coming. So similarly you can go on calculating and you will get these values. So I have done up to 10 times, 10 iteration, and if we plot these values here, we can get, so I need to erase this. Yeah, so we'll get a curve like this. So this blue color is basically denoting the probability of the OK state, and this orange color is denoting basically this portion. So as you can see, the probability of a component to be in the zero state is gradually decreasing, and to be failure state it is gradually increasing. So consequently, if we go for infinite number of cases, then the probability to be in zero state becomes zero as the time goes to infinity, and the failure is going up. This is because these components are non-repairable. So there is no chance that components can come back from failure to success state. So that's why we get this kind of curve. Now, what will be the situation if the components are repairable? In that case, there again we have two states. OK is equal to 0 and failure is equal to 1. Now, like previous case, there is a transition probability to go from state 0 to state 1, and that is denoted by lambda. But in this case, there will be another probability that is going from failure states back to the OK stage due to the maintenance or repair, and that probability is denoted by mu, right? Now, again, this is for the repairable component, so this is wrongly written this term. This is for the repairable component. Now, what is the probability? Again, this probability are given by this p0 is equal to 1. So this is the state. So initially, again, the p0 at 0 is equal to 1, and p1 is equal to 0 is 0. Now what will happen after passing of 1 hour? So suppose this is 0.1 per hour, and suppose this is 0.03 per hour, right? So after 1 hour, some component will go into the failure stage, and what is the probability for a component to be in this stage? So 1 minus lambda into p0 will go into the failure stage, and there are some probability that components which are in failure state will come back from 1 to 0 with a probability of mu. That's why mu into p1 is equal to 0. But um, at the initial stage, the first case, the p1 0 is equal to 0, so it will be only like 1 minus 0.1 into p is equal to 0, so initially it will be 0.9. Similarly, 1 minus mu, so this will be 0.1 up at p1 is equal to 1. We can use this formula and make an Excel sheet similar to earlier case, and we get these values. Now you see the values are decreasing, but they are getting constant after some iteration. So you can see they are getting constant around 0.75, right? And initially there was increase in failure state, but they are also getting stabilized at around 0.248, or we can say 0.25. So if we again plot the curve, so there is an initial decrease in probability, but it eventually getting into a steady state, and same thing happening for the failed state also. So if you run this for infinite number of time, then what will happen? So after some time we get a steady probability. So this is a state 0 probability, and this is a state 1 probability. So for the repairable component we get a curve like this, and for non-repairable component we get curve like this, right? So that's it from this first lecture. In the next state we will see if the two components are in one out of two combination, how the Markov transition matrix will look like. Thank you.